Okay, so today, again, from here on out, I'm no longer going to give you the products. You're going to be predicting those. So you'll just be given the reactants only, and then you need to decide what type of reaction it is, and then that will help you determine what the products, and then write it out, and obviously also have to balance them in most cases as well. So the first one we're going to start with is combustion. And combustion reactions, for our purposes in honors chemistry, we're only looking at what's considered technically complete combustion, where we take any carbon compound and it burns or reacts with oxygen to form carbon dioxide and water. So those are the only products that we're going to use with combustion. There are other what we call incomplete combustion reactions and stuff that we talk about in AP, but for here we'll always form carbon dioxide and water. So again, as we talked about last week with the different types of reactions, so anytime you see some type of carbon compound, and if it's an alkane, you'll be expected to know that formula. If it's not an alkane, I will give you that formula. But anytime you see a carbon compound and oxygen, know that that's combustion, and it's going to form, anytime you see a carbon compound and oxygen, it's combustion, it's going to form carbon dioxide and water. And again, we use combustion reactions all the time, like you're probably not combusting any food right now, but after you eat lunch, you'll be combusting the carbon compounds in your food to give you energy, keep your body warm. We burn wood, other things, to coal to heat our houses or keep us warm, and same thing, even gas as you're driving around. You're burning gasoline. That's combustion, because besides just carbon dioxide and water, it also produces a lot of energy and heat, and that's what heats your house or keeps you warm, or why your engine gets hot in your car. So again, if it's an alkane, you need to know that formula. If it's not an alkane, I'll give you the formula. So like this, for example, methanol. Methanol is not an alkane. So if this were on your homework or test or quiz, I would give you that formula. And methanol is CH3OH. That's what we call an alcohol. It's not the alcohol you drink, although I know you're not supposed to drink anyway. But this will kill you. This is poisonous, and that's actually, it's been a while back. But people who make their own alcohol have to be very careful, because it's very tricky to make ethanol. That's the drinkable alcohol, and if you don't do something right, you'll make methanol and it'll kill you. And a lot of people, somebody made their own alcohol and took it to church and gave it to a bunch of people. This was like 5 or so years ago, and a bunch of people died from it. So there's a little fun fact. Not fun, but and so it burns with oxygen. And again, remember, oxygen's always O2 when it's by itself. And so when you see this, here's my carbon compound, here's oxygen. That means it must be combustion. So therefore, going to form carbon dioxide and water. Okay. So again, I'm not going to tell you the carbon dioxide and water anymore. You'll need to know that when you spot that that's a combustion reaction. And then in terms of balancing, with combustion reactions, we don't have any metals. Now here with this alcohol, we have a hydroxide group, but we don't have hydroxide over here. So you're going to balance those elements individually. So we'll start first with the carbons, because again, we always want to save the hydrogens and oxygens for last. Right now the carbons are balanced. And then what makes these alcohol type carbon compounds tricky to balance is people forget to count the extra hydrogen and oxygen from the hydroxide group. So if we do the hydrogens next, we actually have 4 hydrogens on this side. So to make 4 hydrogens on the product side, we put a 2 there. And then let's take a look at the oxygens. So over here we have 1 and 2. So we have 3 oxygens on the reactant side, but we have 4 on the products. And this is where that rule of, we've got an odd number of, in this case, oxygens. To make it easier to balance, let's double that. So this is the oxygen that's making us have an odd amount. So I'm going to put a 2 in front here. Now before I go back and balance the oxygens, that has changed. That has changed my carbons and hydrogens. So we want to rebalance anything that we'd already balanced. Once we change it, we need to fix it. So now we have 2 carbons. So I'll put a 2 here. And then we have 6 and 2 more. We have a total of 8 hydrogens. And again, that's where a lot of people balance these incorrectly, is they forget to count these extra hydrogens. So we have a total of 8 hydrogens on this side. So let's change that over here to a 4. And now let's check our oxygens. So on this side we have 2 and 2, and then we have 4 and 4. So we have 8 on this side, 4 over here. Now to balance the oxygens on the reactant side, if we change these, that's going to change our carbons and hydrogens, and we're just going to go around and around in a circle. So let's change these oxygens here and make it 6. So now we have 8 and 8, and this is balanced. So if you see a combustion problem with an alcohol, it can be a little trickier to balance, because again, remembering to include the oxygen and hydrogen in the hydroxide. But just take your time, and again, follow that order, and it should make it as easy as possible. Okay, so those are combustion reactions. Now with synthesis, we actually have 4 different types of synthesis reactions. So the first type of synthesis reaction is kind of why they call it a combination, which again, you can call it a combination reaction, that's fine. Just make sure I can tell the difference between, if you write just COMB or something like that, if you abbreviate it, make sure I can tell the difference between, are you talking about combustion or combination? Okay, but I like to use the term synthesis. So this first type of synthesis reaction is where we are combining just 2 individual elements together, and then when they combine together, they're going to form an ionic compound. And remember, anytime we have some kind of ionic compound, we have to crisscross their charges. Okay, and that's where people go wrong a lot with these reactions, is they forget to crisscross their charges anytime we're dealing with some type of ionic compound. Okay, so we can have any combination of 2 elements. So here it says magnesium reacts with oxygen. Okay, now magnesium is metal. It's on the left side of the stair step. It's just plain old Mg. It is not a diatomic. So we just write Mg. But oxygen, just like in the combustion reaction, is O2. Non-metal. And so that's your clue. We have 2 individual elements. Even though this is diatomic, that's how oxygen exists when it's all by itself. So again, they're going to combine and form the ionic compound magnesium oxide, which again, we have to crisscross those charges. So what would that look like when we do that?
MgO2.
Mg what? No. No.
Just O.
Just what?
Just O. It's MgO.
Just MgO. Yeah, because magnesium's +2, oxygen's -2, so the 2's reduce. So again, that goes back to October, whenever, knowing that magnesium being in column 2 is +2, oxygen being in column 16 is -2. Okay, so yeah, got to make sure you're crisscrossing correctly. And then for this one to balance, since we've got 2 here, just put a 2 and a 2, and it's balanced. Okay, yeah.
you not bring like both of the oxygens over and just bring one of them?
Well, now this is only here because when oxygen's by itself, it's diatomic. When it's in a compound, it's, in this case, it's in an ionic compound, it's gonna be its -2 ion, yeah. Okay. Okay, so that's our first synthesis one. The next synthesis reaction is where we are taking a metallic oxide, which is exactly as the name implies. It's a compound made up of a metal and oxygen. Just like here, magnesium oxide is technically a metallic oxide. And reacting it with water, it's going to combine together to form a metallic hydroxide, which the common name for that is a base. Okay, and at the end of the school year, our last unit, we're going to be talking about acids and bases some more. So we'll take a closer look at this type of reaction down the road as well. But again, we've got metallic oxide, that's an ionic compound. Metallic hydroxide, that's an ionic compound. So we've got to be crisscrossing charges with those as well. And again, all of these synthesis reactions, they all form just a single product. Okay, so that is what they all have in common. So if we take a look at aluminum oxide, what's the formula for aluminum oxide?
Al2O3.
All right, very good. Yeah, Al2O3, because aluminum's +3, oxygen again is -2, so we crisscross. And then we have water. Okay, so here's our metallic oxide. And you don't have to label this, I'm just doing this to show you. But this is our metallic oxide, and obviously water is water. So that's your clue that this is a synthesis reaction that's going to form a metallic hydroxide or base. And what would that metallic hydroxide look like? AlOH. 3. Yeah, because again, aluminum's +3, hydroxide is -1. So we need parentheses around the hydroxide, and we have AlOH3. So again, you got to be able to crisscross your charges, and here's our base. That's our base. Crisscross our charges so you get the right formulas, because if you don't have the right formulas, you're not going to be able to balance. And then obviously we need to balance this. So once you get the reaction written out, you know you got your formulas correct. So we'll start with our metal again. We've got 2 aluminums here, 2 aluminums over here. Okay, then our hydrogens, we've got a total of 6 hydrogens on the product side. So let's put a 3 here, give us 6 hydrogens. And then in this case, our oxygen's already balanced. We have 6 over here, and then we have 3 and 3, 6 over there. Okay. So again, just depending on what metal is combining with oxygen, you know, that'll dictate what your metallic hydroxide will be and the balancing and all of that. But again, you got to make sure you're crisscrossing your charges. Anytime we're dealing with a metal, it's an ionic compound, so it's going to need crisscrossing. Everybody see how we got that? Okay, then the next one's very similar to that second one. So this third one is where we have a non-metallic oxide reacting with water. Now, when we have a non-metallic oxide, we're not crisscrossing charges. That's a molecular compound. So that'll be 2 nonmetals. So some nonmetal on the right side of the stair step plus oxygen combined with oxygen. So we'll be using the prefixes. And water, it's going to form an acid. In fact, it's going to form a ternary or oxy acid. So H with a polyatomic ion. Okay. And the nice thing about these is I'm only going to give you, there's only a limited amount of these that I will give you, and they all just, as you'll see with this one, we can combine them together to make the acid, and then those actually already will balance out. So for this example, we have sulfur dioxide. And what's the formula for sulfur dioxide? SO2, yep. And again, there's no crisscrossing. That's just molecular compounds, random amounts of the nonmetals combining together. So we have SO2. Again, you don't have to label this, but that's our nonmetallic oxide. The sulfur's on the right side of the stair step. And then again, water. So, like I said just a minute ago, there's only a handful of these that we'll do because for these to make the acid, the ternary or oxyacid, where it's H with a polyatomic, we've got the hydrogen. We're just going to take everything that's here and combine it together to make an oxyacid. So we have 2 hydrogens, and then we're going to take our nonmetallic oxide, which is 1 sulfur and 2 oxygens, plus this other oxygen over here to make our polyatomic ion. So in this case, that will make SO3. And so the name of this acid would be sulfurous, yes, sulfurous acid. And you don't have to name it, but just to practice. But we come up with what the polyatomic ion is from what's in our nonmetallic oxide, and then we add the other oxygen from water. So there's only a handful of these that I can give you that will work out this way. So any of the sulfates, like instead of sulfur dioxide, if we had sulfur trioxide instead, that's a 3. That's supposed to be a 3. If it was sulfur trioxide, then we take SO3 plus this other oxygen and make it H2SO4, so then that would be sulfuric acid. And really the only other ones that will work out that I would give you are the carbonate ones as well. So again, these will automatically balance because we're just combining everything together into those ternary or oxyacids. Okay, so those are pretty easy, but you're not going to see a lot of them. Then the last type of synthesis reaction is kind of taking these 2 reactions here, these 2 synthesis reactions, and combining them together. So we're taking a nonmetallic oxide and combining it with a metallic oxide, and together those are going to form a ternary ionic compound of a metal with a polyatomic ion. Yeah?
Wait, so what did we have to take for the third one?
Just add everything up. So you see we've got 2 H's, an S, and I changed it to 4 oxygens because there's 3 oxygens. Huh? No, because it'll all balance out. Okay, and any ionic compound we can call a salt. That's just the generic name. But these will combine together, kind of like how we combine the nonmetallic oxide and water together. But this time it will combine to form an ionic compound of a metal with a polyatomic ion. And again, we'll have to, because it's a metal, we'll need to make sure the charges crisscross properly. So here we have carbon monoxide. What's that formula? CO. Yep. So that's our nonmetallic oxide. And it's combining with sodium oxide. What's that look like? Na2O, good, because again, sodium's +1, oxygen's -2, so that's our metallic oxide. And then just like we did for the one that made an acid, we're just going to take all these elements and make it into our ternary ionic compound, which we always write the metal first. So sodium's our metal. It's going to come first. And then we're going to take the non-metallic oxide and the other oxygen. So we have CO here, and then this other O to form CO2. What is CO2? No. Polyatomic wise, CO2 is carbonite. Yeah, carbonite. And carbonite, just like carbonate, has a -2 charge. So this actually is called sodium carbonite. And that's our ionic compound, our metal and our polyatomic ion. And again, we're just taking everything and combining them together. So these two synthesis reactions, you shouldn't need to do any balancing. I mean, this last one, there could be a case where you may need to do a little balancing, but most of the time you should be able to just combine them together. Now, because of that, you're not going to see a whole lot of these. The most common synthesis ones are going to be these first two. So the two elements making an ionic compound, or the metallic oxide and water making a base. Those are going to be 75%, 80% of the synthesis reactions that I give you, because I only have a handful of these that I can do for them to work out. Okay, yeah.
So why don't you take both of the substances, just because you just take them out of the compound and then combine them to form the salt, or?
Well, just everything blends together.
So you just take the metal by itself, even if there's a.
Well, I mean, this is this is a one whole compound here.
Okay.
So the metal just reacts with this non-metallic oxide, and the non-metallic oxide becomes a polyatomic with the other oxygen, and then it forms the salt with that. Yeah. But yeah, these last two, you just smush everything together to make the one product. But again, make sure with the acids we write the H first, and then the polyatomic, put that in normal polyatomic form, and then with this last one we write the metal first, and then the polyatomic ion.
Why does the H go first in acid?
Because H's go first in acids, as we learned back in October, right?
If there was a reason for it.
Just to identify it as an acid, yeah. That's how we, way back when we're identifying acids, yeah. So, yeah, and just like we always write the metal always comes first in ionic compounds. So again, those are all things I expect you to remember back from last semester when we were naming compounds. Okay? Any other questions?